In the subset or feature selection problem, we are interested in finding the best subset of the set of features. And what I mean by best is really that you are looking for the subset containing the least number of dimensions that most contribute to the accuracy of a machine learning algorithm that you have in front of you to work with using that data set. So in this problem, we have our data, so that's a d-dimensional data set, and we plan to use that with a certain machine learning algorithm. And the hypothesis that we have when we deal with this method is that some of the d features are redundant or irrelevant, and they are redundant or irrelevant not in themselves but in the presence of other features. So that leads to the idea that maybe some combinations can be simplified. Having a feature implies that another feature doesn't have to be included. And so the problem is going to be to find a subset of k smaller than the original d features that contributes the most to the accuracy of the machine learning algorithm we are investigating on that particular data set. And the methods that I'm going to tell briefly about fall into this category of wrapper methods, and they are a combination of a search algorithm for features with an evaluation algorithm of each set of features. In these wrapper methods, the data set is split into training and testing, and the search for the feature is done through the training set and the evaluation is done through the test data set. And as a matter of fact, there are also other methods than wrappers, and they don't do a full learning, but rather they measure various things, such as correlations or mutual informations, and they tend to be faster in practice, maybe less informative sometimes, but certainly faster. Also, another class of problems that we mentioned in a different context is that of the regularization approach to linear regression. So that method effectively does a feature selection because it penalizes for more features and only allows them to be included if they contribute to the accuracy of the model. But in this video, I will focus on the wrapper methods, and they go like this. For all subsets of features, the idea is to run the learning algorithm on each one of these subsets and compare their accuracy on the validation set, and just simply select, the best accuracy and select the subset of feature included in that version of the learning model. And so when you do it like this, what you have to do is you have to consider all subsets of features, and there are 2 to the power d such subsets. And in any realistic application, d is going to be too large to be able to do that. In any realistic application, you are going to deal with tens, sometimes hundreds, sometimes even more than that number of features. And so this 2 to the power d is going to be computationally infeasible. So once we realize that this principled approach to the wrapper method is unfeasible, the next best idea we have is that we are going to do heuristics. So if we cannot really evaluate all subsets, maybe we will just do a sort of a heuristic search through these subsets and somehow lead to some of the subsets that are good without having the insurance that really we are going to find the absolute best solution, but we are going to find something that's good, or at least the best in our search. So what I mean by this is that we are going to do heuristics, and the method that I'm going to talk about in this lecture has a name in computer science. These are called, in general, greedy methods. And the general idea in these methods is that we are going to have an iterative step-by-step procedure in which in every step we do something. We either add a feature or we remove a feature. And in each step, we are going to take that particular decision that is going to maximize a local gain in that step. And so here you have it also intuitively why this kind of approach might miss the global optimum. It might miss, the absolute subset of features because it only has access to the value of one feature at a time, and it's going to select all the time the best one in this particular step. But choosing the best in each step doesn't guarantee that you're going to reach the subset that is globally optimum. But having this computational difficulty of not being able to evaluate all of them, this is perhaps the next best thing to do. So this kind of iterative, step-by-step, greedy methods to search in our subsets of features. So for the feature selection problem, we have this approach, forward selection, and there will be one more that I talk in just a moment, but it's going to be very similar to this one. So in the forward selection, what we do is we are going to start evaluating each feature individually. And for each one of these features, we are going to train a model that takes into account the data set with only that particular feature. And so that means that we are going to have, having D features, we are going to have D models, and we are going to select the one with the highest accuracy. And then in the next step, we will say, well, for this feature that we just selected, I would like to see what other features can I add. And so you're going to, again, evaluate all the remaining D-1 features and add them one by one to the feature you selected in the previous step. So this time you are going to evaluate D-1 models, each one of them with 2 features. And again, you are going to choose the one leading to the highest accuracy. So now you have 2 features. And then you continue this step by step. And you are going to stop when the accuracy is going to stop increasing, or it's going to increase too little for your application. So you might have a threshold that you define depending on the application, and then you will say, I found the subset of features that seems to contribute the most towards the accuracy of the model. And you can also do it the other way around. So in other words, a backward selection. So not starting from the empty set and adding features, one by one, but rather doing it the other way, starting from the full set of features and removing them one by one. So in each step, you evaluate all of the features that are still in your set and you remove them one by one, and you train a model for each one of these smaller subsets, and you select the one that decreases the accuracy the most, and you're going to choose to eliminate that feature because it seems to decrease the accuracy the most. And so you are going to stop this procedure in this case when the accuracy stops decreasing or decreases so little that maybe doesn't make sense to continue. And I just want to take this one more time to formalize it a little bit more, and then I'm going to show you an example of how this goes. So the forward selection or the forward search, once again, the idea was that we add the best feature at each step. And the way this goes formally is that initially your set of features is going to be initialized as the empty set. And then in each iteration, what you will do is you will find the best new feature. So in other words, you are going to find that particular J, which minimizes the error of your algorithm on a data set that's represented on the feature set F union xi. So in other words, you are adding just one feature, feature I, to the current set of features. You train a model on your training data set, and then you evaluate the error on the validation set. And then the one feature that minimizes this is going to give you the feature that you are adding in this step. So you are adding xj to f if this error is smaller than what you had before. If this stops decreasing, or again, if it decreases too little, then you stop the whole search and you declare that you found a reasonable subset of solutions. Certainly the best one using this particular search strategy. And so the computational effort of doing that is something like this. First, you have to learn D models, right? One for each feature, and then you select just one feature. Then you evaluate the next D-1, so you have to evaluate D-1 models, and then you have to evaluate D-2 models, and eventually, in the last step, D-K models. And so by the time you have stopped, you have to evaluate D plus D-1 plus D-2 plus all the way to D-K, and that gives you big O of D squared number of models to evaluate. So this is the so-called hill climbing strategy, and so you have to deal with a big O of D squared models to learn. And the backward search, I will not formalize it on this slide, but it's exactly the same idea, except that you start with all the features and you are removing one at a time, if possible. If the accuracy is increased. If it's not increased, then you are stopping. And there are also other ideas, for more sophisticated approaches, in a sense that you don't really have to add one feature at a time or remove one feature at a time, and you can imagine more sophisticated approaches where, for example, you would add several features at once, or you would remove out of the existing features you have, you remove some. And this might depend, on some insight you have on that particular learning algorithm and on that particular data set you have in front of you. It doesn't change the conceptual, difficulty you have. It's still going to be a heuristic. It's still not going to guarantee that you will achieve the globally optimum subset of features. But it might, change somewhat the searching strategy from this greedy to something else, adding and removing more features in each step. So that's something that could also be attempted, and this is called a floating search. But the basic principle remains the same. You have an iterative approach, and in each step you are changing the set of features, and you are aiming for a procedure that at some point converges, and then you declare that it's stopped and you are working with the last subset of features you had. And I want to give you an example of how this would work in practice. And to do this, I'm going to use the iris dataset that we also had in one of our assignments. This is a widely used dataset. So this is the iris dataset. This particular dataset is coming from University of California at Irvine. And this dataset has features of three classes of iris flowers. So we have three classes. And we have four features, and the features are we have sepals and petals, and we have information on the length and width of the sepals and petals for each flower in the dataset. And in this dataset, we have 50 instances per class. And so again, this is something that we've worked with in one of our assignments, and in fact, it's included in the scikit-learn package of Python, and it's also freely downloadable from many places on the web, including from University of California at Irvine. So if we go and demonstrate this feature selection on this dataset, and we take this forward search for a feature. So in the first step, what we will do is we will say, well, I evaluate each feature at once. So for each feature, I'm going to train a model and I'm going to check the accuracy. And I'm just representing in this picture how does the data look like in this top part of the picture. How does it look like when I'm representing it just on feature 1? So in other words, the 4-dimensional data set we have is projected now just on one single dimension, and that's on feature 1. And I show this by dots some of the data we have, and there are 3 types of data, and one class is denoted by this plus type of dot, and there is another class denoted by this red X, and then there is also a class denoted by this blue circle. And the fact that you have some coincidences, it only means that there are samples coming from different classes that on dimension F1 happen to fall in the same place. And the same goes for projecting the data set onto just dimension F2 and F3 and F4. And so we train 4 models, one for this data set and another one for this data set, and one for this and one for that. And the strategy in all these learning models is going to be the same. We are going to take 20 samples from each class for training, and we are going to leave 30 samples per class for the validation. And so when we do this, we come up with the optimal model for each one of these data sets, and the accuracies, as it turns out, for this feature, the accuracy on the validation set is 0.76. And for F2, for this model corresponding to F2, the accuracy on the validation set is 0.57. On this one with F3, the accuracy is 0.92, and on F4 is 0.94. And so our strategy was select the one that gives you the highest accuracy, and that obviously is going to be F4. So you are going to say as a conclusion of this first step that I'm going to select F4 in my subset of features, and then I proceed to the second step. And here in the second step, so this F4, by the way, I'm just writing here, this is the petal width. So you just say, I'm selecting this particular feature. And so in the second step, what you do is you say, well, I already have F4 selected. So F4, in addition to F4, I'm going to evaluate how does it go if I'm adding F1, how does it work if I'm adding F2 in addition to F4, and how does it work if I add F3 to F4. So in each one of these cases, again, I'm projecting our 4-dimensional data set onto these 2 dimensions, and I have the same representation as before, the 3 classes with pluses and X's and circles. And again, the fact that sometimes they fall into the same place, it only means that there are 2 samples coming from 2 different classes that onto these 2 different dimensions happen to fall in the same place. And we are training 3 models, one for this data set, so again for this 2-dimensional data set, and one for this 2-dimensional data set, and one for this 2-dimensional data set. And the accuracies in each case is going to be 0.87, and here we get 0.92, and here we get 0.96. And so again, the forward search algorithm was saying select that feature which maximizes in this particular step the accuracy. So that means that we are going to select this one, and that means that we are going to select F3, and F3 is the petal length. And so now we have 2 features in our set, and we can continue to the next step, but in the next step, in fact, we can see that the accuracy, in fact, stops increasing. And so we conclude that the optimal subset of features, at least in this greedy search that we are doing, is going to be made of 2 features, F3 and F4. And so that's going to conclude our algorithm, and for all practical purposes, then we can just say, it's going to be good enough to project onto just these 2 dimensions. Just one more comment about this example. An interesting observation that we got using just F3 and F4, we got an accuracy of 0.96. And just as curiosity, if you like, if we are using all features, so F1 plus F2 plus F3 plus F4, and we use the very same data set and the very same learning algorithm, the accuracy, in fact, in this case is 0.94. So it can also happen sometimes that dropping features, in fact, is going to lead to a more accurate model. And that's also one advantage of doing feature selection. It makes the decision procedure more focused, and so sometimes less prone to errors.